Hello students, I am Radha Kumari Pani, Assistant Professor at VIT. So last class we have derived the entropy calculation, okay, like the various entropy calculation in different thermodynamic application, like what will be the del S for melting, what will be the del S for vaporization, and what will be the del S for configurational change. There is one equation that is K ln W, okay, where K is the Boltzmann's constant and W is the number of arrangement. So in today's class, we are going to derive the Clausius-Clapeyron equation. The two scientists, one is Clausius and the another one is Clapeyron, has given the most important equation in thermodynamic application. Okay, like what is the application of this equation is by we are seeing some phase changes. Okay, like in water system, there is from ice to water, water to vapor. Okay, solid to liquid, liquid to gas. By this phase equilibrium, how we can interpret the temperature and pressure changes. Okay, the two state variable, the temperature and pressure, how these two quantities are changing by changing the phases. So this equation is derived from we have derived from the last class dz is equal to vdp minus sdt. Okay. So to remember this equation, like this, we have also three equations, like in the form of dH, that is enthalpy, and dA, that is Helmholtz energy, and that is du. Okay, U is the internal energy. So there is a shortcut, student, to remember these four equation, and this four equation is most important because this is application in everywhere. Okay, this equation what I am giving to you now, this will be application in whole thermodynamic part. Okay. So there is one short trick to remember this equation, four equation. Write first this term. Okay, like S, P, T, V. Okay, entropy, pressure, temperature, and volume. And these four quantity, keep the four quantity in the four corner of a box. Okay, and in the phases part, like keep four energetical term like H, Z, A, U. Okay, and like this. Draw the two arrows like this. Tail S and head will be temperature, and this in this corner head will be towards volume and tail will be towards pressure. So first let derive the equation for dH. Okay. So first any like and four phases there is four energetical term H, G, A, U. So first for H always remember to derive the equation always take the opposite phases. Opposite phases two term as there. What? Temperature and volume. And these two quantity will be remain as it is, like temperature and volume. And along the plane, okay, along the same line towards the corner, two quantities are there, pressure and entropy. And that term will be remain as differential term like dp and ds. And another one, it is to remember the arrow towards head, the quantity will be remain positive. If the arrow towards opposite to that head, like tail, that will be keep as negative. And all these four equation I will derive and will get my point, what I am trying to say. So dz will be C. TDS, it is written as it is, and S is the D form, plus V dp. Okay, because the two term towards the head, so it is written in positive form. Like for dz, what it will be? For dz is opposite phase are S and V. So and here the entropy, it is the tail towards. Okay, it is the opposite of head, opposite of arrow. So it will be written as minus S dt plus, because towards the head, V dp, or we can write V dp minus S dt, this equation. Okay. So now the third one is let dA. For dA, what it will be? For dA, the opposite is S and P. So it will be minus P dV, okay, and minus S dt, because the two opposite are opposite to head. Okay, so it will be minus form. Now the fourth one is internal energy, that is du. For the du, the opposite is P and T. So see, T is towards the head, so it will be written as positive TdS minus PdV. Okay, so these four equations, so we can derive from this small trick. Okay, SPTV, and in the four corners of the box write SPTV, and the faces write HGAU. Okay, and for DH it will be DD form, and the opposite term it is written as it is, and the positive negative sign, if the term is towards the head then it is positive, it opposite like this opposite to head then it is written as negative. So now we are we'll derive the Clausius-Clapeyron equation. See, this graph, it is written, it is drawing between the del G and T, gives free energy and temperature, and this four line it is given like for solid, liquid and vapor. Okay, this line is for solid, this line is for liquid, and this line is for vapor. Okay. So consider the melting solid to liquid. If the phase changes from solid to liquid, we know at one temperature, at melting point, okay, at melting point, the free energy of solid, the free energy of liquid will be equal. So del G will be 0. So like this, dGs for the solid we can write Vs volume for solid, dt minus entropy for solid, dt. Like this, we can write dg for liquid. What it will be? VL volume for liquid dt minus SL dt. Okay. So, if we are differentiating equation 1, okay, if you are differentiating this, this is the equation 1 and this is the equation 2. If you are differentiating equation 2 from 1, so what it will be? Vs minus VL dt, that is equal to SS minus SL dt. Sorry, it will be dp. Okay, vdp minus sdt. So please rectify this. It will be dp. So now if we are dividing dt by dp, what it will be? Del ss minus sl means difference. This is the difference between entropy and is the difference between volume. So we can write del v minus del s. So here dt by dp is nothing but this is the rate of change of the transformation of temperature as a function of pressure. Okay, from this graph dt by dp. So final equation we are getting dt by dp is equal to del v by del s, and this is known as the Clausius-Clapeyron equation. Also we can derive another equation from this like this, dp by dt we can write, okay, del s by del v, and from the third law of equation we know del s will be del q by t, and here del q at constant pressure, what it will be? Del h by t. So in the form of del s we can write del h by t del v. Okay, two equation we can derive from this. Also there is one integrate equation, that is ln p2 by p1, that is equal to, also from this equation we can derive the another equation of Clausius. There is a different form of Clausius-Clapeyron equation. Okay, ln p2 by p1, that is equal to del h by r 1 minus t1 by 1 minus t2, and this also equation we can derive if you are taking the v is equal to pv is equal to nRT and v is equal to nRT by p. From that equation we can derive this equation. This is the integral form of Clausius-Clapeyron equation. So what is the significance of this equation? Okay, see, this is the graph, this is the phase diagram of water system, H2O, solid, liquid and gaseous. From this graph we can derive, we can say what is the one term is there, that is degrees of freedom. What is the degrees of freedom and how it is changing from different phases, how it is changing. Okay, first consider, and you can see the slope, that is for solid to liquid. Okay, this is negative. Solid to liquid, this is negative. Why it is negative? We can see del y, if you are taking the slope as del y by del x. Okay, del y by del x, and this is inclined to this. Okay, if you are taking the slope, what it will be? Sorry, the slope here it will be for the solid to liquid slope, it will be negative. Okay, again for liquid to gas, it is slope is positive. Solid to gas, slope is positive. But for solid to liquid, the transition slope is negative. Why it is negative? We can derive like this. See, if the equilibrium between solid to liquid, and all these three phases are remain in equilibrium. Okay, for solid to liquid, if you are taking dt by dp, or we can take dp by dt. So del s by del v. Okay, the slope will be del s by del v. Here the entropy will be positive because if we are taking from solid to liquid, the entropy, the randomness, the independent will be increased, but the volume will be decreased because for the solid to liquid, okay, the volume is del v is equal to v liquid minus v solid, and in the thermodynamic form there is always volume for solid will be greater than volume for liquid. Okay, in material in thermodynamic form always this small changes is there. The volume of solid will be greater than the volume of liquid, so this term will be negative. Okay, and the dp by dt we can write del s is positive but del v will be negative. That's why the slope is negative and the line will be C, like left, some part is towards the left, means del y by del x will be negative. But for the liquid to gas, slope is positive. For the solid to gas, slope is positive. Why? Because the entropy here, the entropy is positive, and also the volume also it will be positive. Because for solid to gas, okay, let's for the sublimation process, the volume of gas will be greater than the volume of solid, and for the vaporization, liquid to gas also, the volume of gas will be greater than volume of liquid. So like this way we can derive why the slope is here negative, why the slope is positive and positive. And one term we can see here from this phase equilibrium diagram of water system, that is degrees of freedom. And now what is degrees of freedom and what is the significance of this term? See, in generally we can say degrees of freedom is nothing but this is the independent variables. Okay, this is the, here it is for the state variable like temperature, pressure and concentration, like this. Okay, independent variables which has freedom to vary. Okay, degrees of freedom, it is nothing but these are the independent variables, or we can write independent state variables which have freedom to vary. If one state variable is kept constant, then another should vary. Okay, and the equation for to calculate the degrees of freedom is known as from like two for the two component system, one component system, that is C minus P plus 2. Okay, one component, why? Because water is one component and 2 is for two state variable like temperature and pressure. This is the equation to calculate the degrees of freedom for any phase changes, like from the solid to liquid, the degrees of freedom will be 1, and from liquid to gas also the degrees of freedom will be 1, and for the solid to gas, for the sublimation process also degrees of freedom will be 1. How? Because see, we can calculate, let for the solid to liquid we are calculating the degrees of freedom. For the component will be 1, and the phases, the two phases are in equilibrium, so in the place of P we can write 2 and plus 2, minus 2 plus 2 gets cancelled, degrees of freedom is 1. But in this point, this is called the triple point, where it is written as T. This is called the triple point. In this triple point, the three phases, you can see the three phases are in equilibrium. Okay, so the degrees of freedom is this point will be 0. How? Because F is equal to C minus P plus 2, and C it is 1, but P will be 3 because solid, liquid and gases, all the three phases are in equilibrium in this point. So 3 plus 2, it will be minus 2 plus 2, so 0. Okay, so that means in this point, okay, this is called the triple point. In triple point, all the for the three phases R will be equilibrium when the temperature and the pressure are kept constant. and they should not be vary. Okay, like in this phase equilibrium, solid to liquid, liquid to gas, there will be 1 degrees of freedom. We can vary one constant, one variables. Okay, but in this point, the temperature and the pressure, the term will have to be, okay, will have to be stay constant for the 3 phases and will be equilibrium. And this is the significance of this Clausius-Clapeyron equation, and we'll get the various application and various numerical type problem from this equation, and the different forms are there, and we'll get mostly like the problem like this: ln P2 by V1 del H by R 1 minus T1 minus 1 minus T2. Okay, so this is the important, you have to remember this equation. So now we are going to what is the thermodynamic parameter, how it is changes in binary system. Okay, from the last class we have discussed about the in single component system, what are the phases, what are the changing. In today's class we'll derive the how the parameter changes, like del H melting, del G del H mix and del G mix in binary system. Binary system means 2 components are there. Okay, let's consider the 2 component A and B. Okay, are in if we are mixing the 2 elements A and B, what is the mole fraction of XA and what is the mole fraction of B? It will be the mole fraction of A will be XA, because any mole fraction, it will be number of moles by total number of moles. Okay, initially it is A and B, so the number of moles is Na and Nb. After the mixing 2 element, what will the mole fraction of A? Na by Na plus Nb, and similarly we can write what is the mole fraction of B? Nb by Na plus Nb. Okay, so here we can write this is the before mixing. Okay, after mixing this will be the mole fraction, and Ga will be Gibbs free energy of A and Gb will be Gibbs free energy of B. After the mixing, the total Gibbs free energy will be G naught plus del G mix. Okay, G naught means the initial the free energy, and del G mix means the free energy after mixing. Okay, we can derive. So see, what will be the G naught? G naught will be total Gibbs free energy, means Xa into Ga plus Xb into Gb, means mole fraction of A into Gibbs free energy of A plus mole fraction of B into Gibbs free energy of B. So the total free energy after mixing, that will be G naught plus del G mix. Now we get G naught from this, and now how we can derive the del G mix? Okay, see, first del G mix, from this equation we can derive the del G mix will be G minus Z naught, and also we know Z is equal to H minus Ts. Okay, so for G will be H minus Ts, and for the G naught will be H naught minus T S naught. Okay, T is kept constant. So del G mix will be, if you are taking the common, H minus S naught means del H mix, S minus S naught means del S mix. So if we are knowing the del H mix and del S mix, we can calculate what will be the del G mix, means Gibbs free energy after mixing the 2 binary elements A and B containing with mole fraction Xa and mole fraction Xp. So let us first determine the enthalpy change because of mixing, that is del H mix, and the change of entropy because of mixing, that is del S mix. See, now after mixing we are taking the 3 assumption. Okay, in thermodynamic calculation we are taking the 3 assumption, that is the molar volume does not change, the initial volume, and after mixing the final volume should not be changed, that will be equal, means V initial volume should be equal to Va plus Vv. Okay, and the bond energy should not be changed between Aa and Bb by the do not change with the change in composition. Okay, the bond energy between A and the bond energy between B should kept constant. This is the second assumption. And the third assumption we are taking, we are neglecting the role of other energy. Okay, only the bond energy is there between the A and B, other energy we are neglecting. So after the mixing, before the mixing there are 2 bond energy, like the bond energy between A and the bond energy between B. But after the mixing there will be another type of bond energy is there between A and B. Okay. enthalpy of mixing can be expressed N0 Z XA XB del E. What is N0? N0 is the Avogadro number, okay, and Z is the coordination number Cn. And XA and SB we know the mole fraction of A and B, and del E is the bond energy difference between AB. And in the mathematical form we can calculate the del E, that is equal to bond energy between AB minus half of bond energy of AA and BB. See, from this graph we can interpret like this is the 2A and this is the 2B term, and this is the interaction between AB. This is the bond energy between AA and the bond energy between BB, and this is the bond energy between AB. Okay, so we can write the del H mix. This is the ohm like one constant. Okay, N0 Z and del E. We are taking this whole as a constant, then XA into XB. Okay. So now del H mix will be ohm some constant XA into XB. So see, we are taking the three situation. First situation, let del H mix will be 0, and the second situation, let del H mix will be less than 0, and the third situation we are taking, let del H mix will be greater than 0. Means after the mixing the enthalpy will be 0. After the mixing, how the enthalpy varies towards negative side and varies towards positive side, this will be term depend on the bond energy. Okay, this whole term will be depend on the bond energy. If the bond energy before the mixing and after the mixing is equals, mean AA and BB is equal to bond energy of AB, then the del H mix will be 0. If the bond energy gets higher than before the mixing, then del H mix will be greater. And now the third situation is, if the bond energy is weaker than the initial, then the del H mix will be less than 0. And this is the third total three situation we are taking. The enthalpy of mixing is 0, the enthalpy of mixing is less than 0, and the third one will be the enthalpy of mixing is greater than 0. How we are taking? That means the AB. Okay, the bond energy of AB will be bond energy of AA plus bond energy of BB. Now the second situation less than 0 means AB will be less than AA and BB. And the third situation, the bond energy of AB will be greater than bond energy of AA plus BB. Okay, so these two situations, the last one, see, why the bond energy of AB is less than the bond energy of BB. These two situation will try to say the transformation is exothermic or endothermic. If the del H mix is less than 0, means the bond energy of AB, okay, is less than, means it will be easy to form. The transformation is getting easy, means this is the exothermic process, means the del H mix is less than 0 means some energy it will be evaporating to surrounding. Okay, the reaction is spontaneous. So we can say this is the transformation is exothermic process. Now the third situation, if the bond energy will be greater, means the transformation it will be difficult to form. Okay, the initial bond energy is greater, means if you are breaking the bond AA and BB, it will be difficult to form the bond between AB. That's why the bond energy of AB is greater. So this is the endothermic transformation, means we are giving some energy to perform the transformation. Okay. So see, so we can see from this graph, if del G mix is less than 0, del G mix is equal to 0, and del H mix is greater than 0. From this graph also we can see. Okay, means the bond energy of AA and AB will be equal, and the bond energy AA, BB are equal, and here it will be del H mix, means AB is equal to AA plus BB. So now we are taking one term. So finally we are getting the equation del H mix. Okay, del H mix will be ohm XA XB. So XA, okay, XA we can write XA we can write 1 minus XB, because the summation of two mole fraction will be 1. So we can write XA, that is 1 minus XB into XB. So this equation will be XB minus XB square. Okay. So where the enthalpy will be maximum. Okay, at what composition of, let the composition is changing from 0 to 1. XB from 0 to 1 and XA. This is the XA. Okay, one point is there will be maximum point. Okay, so how in mathematical how to derive the maxima? If you are differentiating the term del H mix by xb with respect to xb is 0, then you are getting the maxima. So put the differential equation, see, xb and minus xb square, differentiation of this with respect to xb. So this is the constant, take outside, and differentiation of xb will be 1, and differentiation xb square means differential equation what will be x square by dx, 2x, no, means xn is equal to nx to the power n minus 1. So it will be 2xb, that will be 0. Okay, so from this we can derive 1 minus 2xb is equal to 0. So 2xb 1 and xb will be 1 by 2, that is 0.5. Means at 0.5 molar composition the del H will be maxima. Okay, see, this implies the xb is 0.5, that means the maxima or the minima will be at 0.5 molar composition. Okay, so this, like this we can derive the maxima and minima. And now we are derive first for the del G mix. We have two quantities to derive. One is del H mix and another one is del S mix. Here we have derived the del H mix. Now for the del S mix. For the del S mix, we are taking the configurational changes equation, that is K, L and W. Okay, it will be K, and K is the Boltzmann's constant, W is the arrangement. So del S mix will be S minus S naught. So S naught will be for the, you know, for the pure element the configurational changes will be 1. Only one the configurational figure. So ln 1 will be 0, the final equation will be K, L and W. And the L for the W is the number of arrangement. We are calculating this equation by Na plus Nb factorial by n factorial into Nb factorial. And the one is Tauriel approximation is there if ln n factorial is equal to n ln n minus n. From this equation, we can write W is the Na plus Nb. This equation is see, from the last slide we can derive. If the in the terms of n there is Na plus Nb factorial. So Na plus Nb ln Na plus Nb. Okay. From this Stirling approximation, we can finalize. We can derive the last equation. It will be K N naught, that is Avogadro number, Xa ln Xa plus Xb ln Xb. From this equation, we can derive the final this equation. So the final equation for del S mix will be Kna will be gas constant minus R Xa ln Xa plus Xb ln Xb. Okay, so this is the final equation for del S mix. So now you have the two term del H mix and del S mix, also we can derive the del G mix. So this how the thermodynamic parameter changes in binary system. If two elements are there, let A and B, and then more fraction is Xa and Xb. Like this we have derived the equation. Okay, so from today's class, we have derived first we have derived the what is Clausius Clapeyron equation, how the slope changing in solid to liquid, liquid to vapor, and solid sublimation process, that is solid to gaseous phase. And the second one we have derived how the thermodynamically parameter changes in binary system. In next classes we are going to discuss one is the most important topic in your phase transformation, that is carbon solubility in iron. Okay, so for today this much. Thank you so much.